Hi folks, we are going to continue the chapter 2 lecture in this video, and actually we're going to pick up right where we left off in the part 1 video. We were talking about how to calculate atomic mass, which is the number that is at the bottom of the square in your periodic table. So right here I just have bromine. The top number, I'm grabbing it from the periodic table, is 35. And as we learned in the last video, that is the number of protons. This is the mass of a typical bromine atom. Now, when you think of it as atomic mass, this is the number of AMUs. AMUs being the number of atomic mass units. Atomic mass units are just they're just a mass unit. Just like gram is a mass unit, you can weigh something in grams. That's a unit for mass. Atomic mass unit is another one. It's just like gram conceptually. However, it's much, much smaller than a gram. And it's preferred for measuring things that are really, really small, like atoms or molecules. So that's how much a typical bromine atom weighs, 79.904. Now, what I'm going to do with you on the board right here is question number 77 from the back of the book, or sorry, from the back of the chapter. So if you could turn there now, and if you don't have access to it right now, I'll just read you the question out loud. It's just another type of atomic mass calculation question coming at it from a slightly different angle. So I want you to also see that sometimes the atomic mass calculations are presented a little bit differently, and you really need to be able to handle both styles of question. Okay, so question number 77, I'm in this part of the chapter 2, the back of the chapter. It says bromine has 2 naturally occurring isotopes. These are the 2 isotopes, bromine 79 and bromine 81. Remember from the last video that this number here is the mass number. The mass number is the total number of protons plus neutrons. So if I was to ask you a question, how many neutrons does this one have, for instance, you would just take this number and subtract out the protons. So 81 minus 35, that means it would have to have 46 neutrons. And this one has 2 fewer, 44 neutrons. But that's not what the question is about. But I just wanted to kind of remind you what that number is. In the question, it says bromine has 2 occurring isotopes, naturally occurring isotopes, this one and that one. And it has an atomic mass of 79.904. Now, I wrote this before the video started, 79.904. That's what the question says. It's giving us 3 decimal places. Just so you notice, in the textbook on the periodic table, when you find bromine, you're not going to see all 3 decimal places. It's going to say 79.90. It's okay. It's just rounded a little bit more on that periodic table. And in the question, they give you an extra decimal place. No problem. You just use whatever is given to you. All right, so the question then says the mass of bromine 81, this one, so I'm going to just kind of gather my information here, is 80.9163 AMU, atomic mass units. So, and then it says, and its natural abundance is 49.31%. 49.31%. And then the question says, calculate the mass and natural abundance of this one. So the question wants us to get his mass and his natural abundance. So you can see it's a slightly different type of question than the one that we did on the part 1 video, where you were asked to calculate atomic mass. This time we actually are given atomic mass and trying to find out information about the specific isotope. Now, the setup of the math is exactly the same, where atomic mass is written here. But this time, this is the one that we know. So we're going to write 79.904 AMUs. Atomic mass is going to equal the contribution to the weighted average from the first isotope. We're going to write that part here. And to that, we're going to add the contribution of the second isotope. And that part we're going to write right here. If there was a third isotope, you would just add his contribution to the weighted average. So let's see what we have here. We have information about the second isotope. You can see actually we have all the pieces for this part of the math here. we have the natural abundance, which is 49.31%. We're going to turn that into a real number by dividing by 100, because a percent means per 100, 0.4931. And we're going to times that by his mass. Now, in the previous video, we were just using the mass number to estimate the mass. I think I had you just use that in the AM units in the previous video when we were doing the carbon. In this question, we're giving this very detailed, very accurate mass. This came from a mass spectrometer. If you are given these very detailed, accurate masses, you'll see it's pretty much close to 81. It's very close to 81. But it's more, it's not an exact, each proton and neutron only weighs approximately 1 AMUs. So if you have to estimate, you just go for it. Each one is 1, so this would weigh about 81. But if you're given data from a mass spectrometer, use it, okay? Don't just round it. So we would just go ahead and use that mass. That would go right there. Now, coming over to the first isotope, it looks like we don't have either of the pieces. So that seems like a problem, because with algebra, you really can only have one missing thing. However, you do actually know the percent abundance of bromine 79. It's actually easily implied. And let me go ahead and just say this. If there are only 2 isotopes, okay, we're talking about what percent of the whole is this one versus that one. If this one represents 49.31%, this represents the rest of 100%, because there's only 2 of them. So you're talking about what share of 100% do they each have. So to get his natural abundance is very easy. We're going to take 100 and we're going to subtract 49.31. He is 50.69% of all bromine. If he's 49.3, he's 50.69. So that part is actually known, 0.5069. The only thing that we don't know is his mass, and that is what I'm going to use in X for. That's the one thing that we don't know. And if we can solve for X, we will solve for his mass. Remember, it's the percent abundance times the mass. So now we just have to start simplifying our equation, because we have all the parts. Let's go ahead and do this part first. 0.4931 times 80.9163. So I'm getting 39.899. Now, here's the thing. Let me show you something important about chemistry and calculators and rounding and all that stuff. There are a ton of decimal places, okay? You don't have to spend your time recording all those decimal places, because this calculator will save this information as the, and call it the answer to the previous, or it will call it the answer as we keep doing our calculations. So I'm just going to write a few of the numbers down just to kind of keep track of it. Let me just stop here. Record a few extra numbers, more than your instinct tells you to. Don't be too kind of loose with it. Don't just round everything to like 39.9. That would be too loose. But don't also record all 8 decimal places. That's unnecessary. To be a happy medium. Let me go ahead and just draw the rest of this down here. And then this, of course, becomes 0.5069x. Now, to isolate x, we're first going to have to get rid of this piece algebraically. This needs to be dealt with first. 998. So that will subtract from that side and then also subtract from this side. Remember, in algebra, whatever you do to the left, you've got to do to the right. What I want to show you is that if this is still in my calculator, which it is, if I just kind of leave it there and just start typing something else, so now I've got 79.904 minus, so now I'm trying to do this part in my calculator. If I just do second negative, I can get that answer function. And that will keep all the digits. See, it limits how much you round, and it limits how much error you introduce into all your calculations. And now I'm getting 40.004 with a few extra digits, but I'm not going to write all of them down. Just write a few of them down so you can kind of see what it is. But even again, next step algebraically is to divide both sides by this. We're trying to solve for x. We're trying to get the mass of the number. But I still have all of those digits. See, I don't want to lose good information. I don't want to lose good math numbers here. I have all of them. So now I'm going to divide by, answer divide by. See, all I did was press divide. And then the 0.5069. Now, before you hit enter, think about what the number should be, okay? We're trying to get the mass of this isotope. We want to always think, are we getting a reasonable number? How much should it weigh? Because if you enter something wrong, you should have some sense of that number doesn't make sense or that number does make sense. If bromine 81 weighs about 81 AMUs, which it does, certainly bromine 79 should weigh about 79 AMUs. Because remember, each proton and each neutron is one atomic mass unit, so it should be around 79. Now, not exactly, because it's not that perfect, but it's close. Let me go ahead and press enter, and I do. I get 78 point, actually, let me write the answer up here, because this is the answer. 78.9, and I would have to ask you how many digits to present or how many decimal places. The thing is that we haven't talked about sig figs yet, so we're not going to worry about that quite yet. Let's just do 2 decimal places. 78.92 atomic mass units, and that is the answer, or at least it should be. Certainly you can see that it's very close to 79. You can always check the answers for all the odd number questions in the back of the book, Appendix 3, and you should be doing that as you are learning the material. So that is another angle that these questions can be, where you're given the atomic mass up front of the element and you're asked to find one of the pieces of one of the isotopes. Just kind of another angle. Chemistry is all about asking questions from different points of view, really to test that you understand the concepts and that you're not just kind of memorizing a series of steps, because that's not really learning, that's just memorizing. Okay, so we have talked about isotopes. We talked about what atomic mass is. We are now going to move on to another I word called ions. So ions, an important word in chemistry. So let's go ahead and talk about what ions are. Ions are charged particles. Charged particles that are formed when an atom either loses or gains electrons. Now, here's one very important thing of chemistry. Electrons are the currency. Currency, you think of money, right? The currency of chemistry. Electrons are the particles on an atom that can come and go. Remember, we learned about the atom last time. The atom, the protons and neutrons are safely inside that nucleus. It's the electrons on the electron cloud, the outer part of the atom. Those are the one atomic particle, unless we're talking about nuclear chemistry, which we're not in this course. We're not talking about radioactivity or anything like that. But normal chemistry, it's the electrons on the outside of the atom that can be lost, or that can be gained by an atom, or that can be shared, which is what we'll learn about with covalent bonding. Those are the things that can come and go from an atom, the electrons. And when you lose or gain them, because they have a charge, you'll see that atom end up taking on an overall charge. It won't be neutral anymore. If it loses or gains electrons, it will not be neutral if it used to be. Okay, and remember, the word atom implies neutral. If it's not neutral, you start to use the word ions. So let me go ahead and say a couple things about ions before we even get into, well, actually, let's go ahead and say this. So let us give a bullet point here. Ions can be either monoatomic or polyatomic. Now, not memorizing too much, using your common sense. What number does mono make you think of? Hopefully it makes you think of one. One atom ions. Okay, so monoatomic ions just exist of one atom. So let me go ahead and give you some examples. Cl minus is a monoatomic ion. It's a one atom, but it has a negative charge. And by the way, negative means a 1 minus charge. Another monoatomic ion would be something like S2 minus. One atom, this one has a 2 minus charge. Another example would be Ca2 plus. One atom with a charge. Those are monoatomic ions. Polyatomic ions, the ones that you have memorized on that list, are ions that consist of multiple, poly means multiple, atoms. So ions that consist of multiple atoms. And you learned a bunch of them. So one was, for instance, SO4, 2 minus. So it's a single particle, but it has multiple atoms in it, and it has a total charge of 2 minus. So this is the sulfate ion. I want you to just make sure that a lot of people kind of have a hard time conceptualizing what a polyatomic ion is. So let me take a moment and just draw it for you for a second. It's a molecule. It's a molecule that has a charge. So you've got a sulfur atom, you've got 4 oxygen atoms attached to it. Don't worry about how they're attached. So it is a molecule. They're all bound to each other, but the whole thing is not neutral. The whole thing carries a 2 minus charge. And it's a particle, kind of operates as a whole unit, and it has a 2 minus charge. Let me draw another polyatomic ion for you here. How about something like Cn minus? I think that's on your list as well. That's cyanide, okay? It is a molecule with a charge. So it's a carbon atom attached to a nitrogen atom. The whole thing has a 1 minus charge, or just a minus charge, and it operates as a whole unit, okay? When it kind of forms chemical reactions, unless certain special things happen, it's going to kind of travel together, okay? It's going to do its thing together. Same here, it's going to kind of stay together and operate that way. So that's a polyatomic ion. And with the polyatomic ions, you just want to memorize the charges, because it's not easy to figure out what the charges should be. We'll talk about how I knew that these charges were those numbers. We'll talk about that soon. Okay. So that's ions can be monoatomic or polyatomic. And let me go ahead and kind of give you what you need to know at this point about ions. Actually, you know what? We haven't talked about that part of the periodic table yet, so I'm not going to say that. Let me just go ahead and say, how are they formed? Let's give a little bit more information about how they're formed. I kind of mentioned it up here, but let's give an example. So let's go ahead and talk about sodium. When the sodium atom meets the chlorine atom, okay? Kind of see what happens here. We're kind of building layers of chemistry here, because I can't tell you everything that you need to know yet, but I'm trying to tell you only what you should know at this point. So when sodium meets chlorine, there is a transfer of an electron. So let's go ahead and just set the table. Let's talk charge. Now, if you have a sodium atom, the overall charge is 0. A sodium atom is always, if it's an atom, which it is, because I haven't written anything with a charge, that means it's a neutral charge. Let's talk about how many protons and how many electrons it has. So you actually should know that at this point. So now let me back up. You will always have access to your periodic table, even on the on-campus quizzes. You'll always have a periodic table. There's never an expectation to memorize the periodic table. So sodium, go ahead and find it. You'll see it's atomic number 11. So that means it has 11 protons. Now, the sodium atom, if it's neutral, must have an equal number of electrons. Otherwise, it would never be neutral. Because remember, protons all have a +1 charge. Electrons all have a -1 charge. So you have to have the same numbers of both to get overall zero charge. So that's what sodium brings to the table. Let's talk about chlorine. Chlorine, atomic number, see if you can find it over there on this side of the periodic table, 17. Chlorine has 17 protons. The chlorine atom will also have 17 electrons. Now, when these two atoms meet each other, there will be a transfer of one electron. How do I know that? You'll know that soon as well. But for now, just accept it, that there will be a transfer, and the one who's going to lose the electron is going to be the sodium. You will know that, the Y's and all of that soon, but for now, all I'm trying to get you is to look at the numbers. If you could just trust me on that, I just want you to look at the numbers with me. So sodium is going to lose the electron, lose one of his electrons, and chlorine is going to gain that electron, transfer. He loses, he gains. Let's think about what happens as a result of that transfer. The sodium still has 11 protons, because remember, the protons are safely in the nucleus. They do not leave anywhere. They don't come and go. They're not a currency like electrons are. However, he used to have 11, but now one is gone. He now has 10. So if sodium has 11 protons and 10 electrons, I hope that you can think with me that his overall charge is no longer neutral. He actually has one extra proton compared to his electrons. That's how I think about it, because each proton will kind of cancel out each electron, but there will be one that doesn't get canceled out, and he will kind of remain. And that means this sodium will now have a 1+ charge, or what most people just say is Na+. That right there is what you would call a cation. A cation, or cation, is a positively charged ion. Positively charged, and I see a T right there, I think positive. So positively charged ion. That is a cation, and you would actually call him the sodium cation. That would be the right terminology for that. Let's go ahead and see what happened to chlorine. Chlorine still has his 17 protons, but when this transfer takes place, and the whys of it we leave for later, but just trust that it does, he now has 18 electrons. No longer is he a neutral atom, he is now an ion. Now, what would his charge be? He has one extra electron, and that would give him a negative charge. That's, like I said, that's how I think of it. If that is not clicking with you, because I've had so many different students with different minds and different ways of seeing things, you certainly can just add those two numbers up together. We're doing a positive 17. So just do 17, don't do positive, just do 17. That's going to give you 17 positives plus a negative 18, because remember, electrons are negative, and you will get -1. 17 plus -18 is -1. If you prefer to do that, that's fine, but better to just conceptualize it. This here is what you would call an anion. An anion. An anion is a negatively charged ion. All right, as long as it's negative. Now it can be negative, it can be 2-, it can be 3-. Well, over here, cations can be 1+, they can be 2+, they can be 3+. It just, as long as it's positive, it's a cation. As long as it's negative, it is an anion. So that's what an ion is. It's just it's a positively or negatively charged particle. All right. We obviously will spend much more time talking about ions, but at this level, that's really where we're just going to leave that alone. Alrighty, so let us go ahead and just do a little practice. What we want to do is practice counting subatomic particles. Making sure that this skill is something that we're good at. Let me go ahead and put some symbols on the board. So this is arsenic, 75, 33, with a 3+. Now, once again, this number up here is the charge. The charge, the mass number, the atomic number. Let me move that light so it doesn't shine right there. Okay, let's do 2 more. S, that's sulfur, 3216. And how about Te? 128, 52, 2 minus. Now Te I think is tellurium or something, but like that's not one that you would, that's on your list of memorization. So wouldn't expect you to know that. I could even be wrong. I think it's tellurium, but anyhow, arsenic and sulfur are on your lists. What I would like you to do is take a few seconds and tell me the number of protons, the number of neutrons, the number of electrons, and the overall charge on each particle. So we've got 3 different particles here. 2 of them are ions. 1 of them is an atom, with an ion just being a charged atom, basically. All right, you can pause the video if you don't want to see me do it yet, if you want to just practice it, but I'm going to go ahead and do this in the order that I would do it, in what I think is easiest. So let's do overall charge first. It's just written. So if the charge is written as 3+, you would just write 3+ there. This, what I wanted you to see, if you don't see anything, it's not that I forgot to write something. That is just meaning that there's 0 charge, or probably the word neutral is more what you would say there. But if you don't see anything, it implies that it's a neutral situation. And here it is a 2-, so that means it is an anion. That's a cation. All right, next easiest thing is, I think, protons. 2 ways to find the number of protons. For one, if it's written in this form, the atomic number is right there for you. But also understand that you could just look up the symbols. So As, arsenic, if you find him on your periodic table, you'll have it confirmed that he is 33, which means he has 33 protons. And sulfur is 16, and this one here is 52. So the number of protons is pretty easy. Number of neutrons is also quite simple, because that number up there is the mass number, which is the protons plus neutrons. So if he's the protons, the neutrons would be the rest. So really what you just have to do for neutrons, if you're presented the isotope in this form, just do a little subtraction. The neutrons will be the result of the subtraction. So 75 minus 33 is 42, 16, and this one, 76. So wait, make sure I have these right. 42, 16, and 76. Yeah. Okay. Number of electrons, probably the one that just takes a little bit of the most concentration. Let's start with this one. That's the easiest one. If it's neutral, the number of protons equals the number of electrons. They have to be equal if it's neutral, because that's the only way that you get 0 charge. So that's the easiest one. With this one here, if you have a 3+ charge overall, that means that you really have 3 more protons than you have electrons. The protons are winning. They have more, 3 more. That's how you got a 3+ charge. So that proves to me that this must have 30 electrons. I think that's the easiest way to think about it. And then this one here, if you have a 2- charge, that means the electrons are winning. There are 2 extra electrons or more electrons than you have protons. So if you have 52 protons, that means you must have 54 electrons. That's the only way that you would get an overall 2- charge, because each of those extra electrons would be a -1 charge. So 2 of them gets you -2. All right, so that's counting subatomic particles. Let's keep on moving on to the next part of chapter 2 that we want to talk about. Really, the only other parts of chapter 2 that I really need to get into is the periodic table, what it is, the geography of it, but like really what it represents, and then also learning about what a mole is, what the whole concept of a mole. So let me go ahead. I'm going to just show you a couple pictures first. ones that I would have shown in class if we were in class. So let me write a little bit on the board. Let's do a little heading, the periodic table. So in a way, the periodic table, a lot of students think that the periodic table is a man-made construct, something that scientists invented or kind of decided to gather in a certain way. It's actually an incorrect way of thinking about the periodic table. The periodic table and the fact that you have this very organized arrangement of the atoms is actually something that was discovered. The periodic table existed before humans knew that it existed. It was actually discovered that the elements have this very organized arrangement in their in how they relate one to another. So really the first bullet point that I want to write down is the periodic table was really discovered by a person called Dmitri Mendeleev. There's a picture here of Dmitri Mendeleev in your book. There he is right there. And in the picture, it's kind of interesting because you see him thinking. And really, that's what I'm saying. Dmitri Mendeleev took what he knew about the elements, thought really hard about what he knew about them, and figured out that they were ordered. That's a really cool thing about the periodic table. Now, let's talk about what are we talking about? What was he thinking about? Let me go ahead and tell you what Dmitri Mendeleev did. So let me just do DM. What Dmitri Mendeleev, that's Dmitri Mendeleev's initials. What he did was he listed the known elements. And by the way, at the time that he figured out this whole thing about the periodic table, what we call the periodic law, it's essentially the same thing, but they knew about many of the elements. I don't know how many, but it was a good portion of them. They were able to understand that hydrogen and helium were different. They were able to understand the difference between sodium and potassium, many different things about them, how much they weighed, what type of compounds they made, what type of state they existed in at room temperature, that kind of thing. The type of chemical reactions that they underwent. They knew a lot more than you would think. But what he did was he listed the elements in order of increasing mass, and he discovered, or he, I guess you could say, no, let me use a better word, and he realized that certain sets of properties, certain characteristics recurred periodically. So it's a little bit hard to understand, but let me go ahead and write one more thing on the board, and then I'm going to show you some pictures. This is what he deemed periodic law. Remember, a law is something that nature seems to obey. It's kind of written down, and the molecules obey it, the atoms obey it. This is something that he discovered that atoms seem to obey. They had these certain properties that recurred periodically when you arrange them in order of mass. So let me see if I can explain this just with the pictures that I have. So I think it's better than trying to show slides and stuff. So also, I really encourage you to read this book, especially, you know, all of it, to be honest, all the chapters we're doing, but these early chapters are so fundamental. You don't want to skip over trying to understand that presented. See, the author presents it like a story, which it is, and so don't miss out on the opportunity to actually read that story. It's fascinating. All right, so this part at the bottom, it says the periodic law. What he's doing here is arranging the elements in order of their mass. That's all he's doing. He actually wrote them down on a piece of paper in order of their mass. They at the time knew that hydrogen, I know it's really small, but that says hydrogen, was the lightest element. It didn't weigh much. They knew that helium was the second lightest element. element, then lithium, then beryllium, and so on. So he arranged them in order of their mass, and he noticed something really interesting. I wish this was bigger. We're going to focus just on the greens for a minute. Maybe if you have your book out, you can look at it with me. It's on page 65. Helium is listed in green. What he noticed was that he knew that helium was a unique element. It didn't really form chemical reactions, or it didn't undergo chemical reactions. It was a gas at room temperature. Those were kind of two really big properties about helium. And then he noticed that when he counted 8 spots, he landed another very similar element, neon, also a gas, also very unreactive. And then perhaps a voila moment, when he counted 8 more, there was argon. The other of all these elements, those were the 3 that were gases at room temperature, but also very unreactive. They didn't form ions, they didn't form compounds. That is what he's talking about. This concept of recurring periodically. You have 8 element stretch, and then you reach another element that's super similar in various properties, and then another 8, another element that's super similar. Another example, just to see if you make sure you get the point. Let's look at lithium. Lithium is in light blue. Lithium, at the time Dmitry Mendeleev was doing these studies, knew that lithium was very explosive. If it touched water, it would explode violently. He also knew that it would form compounds with nonmetals, okay? When he counted 8 elements, he found an element very similar to lithium, sodium. It did the exact same thing with water. It formed the exact same type of compounds that lithium did. And then the proof just keeps on coming. 8 more, there was potassium. Potassium being of that list, those were the 3 that were very similar. So he sees that there are these groups, but the groups appear periodically when you arrange them in order of mass. That's periodic law, this order to the elements. So what he did, this is the part that I suppose you could say is a human thing. He just took them and he picture that like a shoestring, and he just wraps them so that the ones that appear periodically are in a column. That's this picture. If you can just picture it spatially, he's taking that long string and wrapping it so that all the greens end up on the, kind of pinching it in the greens and then continuing to wrap the other rows. That is how the whole periodic table ended up getting formed. And what was really neat about it is at the time there were unknown elements that they hadn't discovered yet, but they knew certain properties about them even before they discovered them, because they knew that they would be similar to the ones that fell in the same column. Because once this concept of periodic properties was understood as a law, you knew nature was going to keep obeying it. So it's just fascinating how that was all discovered. So Dmitry Mendeleev was the man. He discovered it. This concept of the elements having these periodic properties, and then that they just started arranging it in what we call the periodic table. But really the order, that's what I'm saying, is not something that man invented. That was all there before anyone discovered it. Very cool. So now let's get into the parts of the periodic table. I suppose you could call this the geography of the periodic table. Knowing it and knowing how to read it and glean all the information that you can from it is essential, obviously. So let me go ahead and draw a periodic table. Let me see, I want to draw it as nicely as I can. Not being too exact with it, but something like this. So if you're trying to do it as well, go ahead and do that with me here. And then there's these bottom 2 rows down here. So the geography of the periodic table, I think it's good to just try to draw it in your notes, or what you could do is print out a periodic table and just write on it if you'd like, and draw with markers or colored pencils or whatever you want to do. So, all right, the first thing that I like to start with the periodic table is helping you see this zigzag line that's here. That's good enough. The zigzag line is very important, okay? Because what it does, it's like a border between 2 parts of the periodic table. All of the elements that are to the left of the zigzag line are called metals. And what you'll notice, if you look really closely, just no matter what periodic table you have, this one here, you'll see that these bottom two rows have like an arrow connecting them to this section of the periodic table. So you'll see kind of like this. So technically, they are all kind of inserted into this section, so they are also metals. These are also metals because they're kind of in this little insert. The reason it looks like that has to actually do with quantum mechanics and orbitals and things, which you will learn later in the course. But for now, these are also metals because they're coming kind of out of this section. Anything to the right of the periodic table are called nonmetals. So the metals versus nonmetals concept is huge. So let's go ahead and give you a little bit about what is a metal. I mean, other than the fact that it's to the left of the zigzag line, what is a metal? What are some of the properties? And then we'll talk about nonmetals. So most important things, metals. Metals are good conductors of heat and electricity. That's why you would use metals not only for electrical work, you know, copper and that kind of thing, but also cooking. You're going to use aluminum, which is to the left of the zigzag line. You're going to use iron. You're going to use copper. Okay, so that kind of thing. Metals would conduct heat or electricity very, very well. That's the first thing. Let's see. Metals also have, let me write the words display, two kind of properties, malleability. Malleability means that you can hammer them into sheets. If you remember Rutherford's gold foil experiment, gold doesn't naturally occur in this beautiful sheet. They hammered it into a sheet. When you use aluminum foil, that's not a natural way, it's not a natural look for aluminum, but aluminum can be hammered into sheets. All the atoms, you can just hammer them until they kind of lie really flat and thin. That's what malleability means. And then also ductility. Ductility just means that you can form metals into wires, and we are familiar with metals and wires. If you go to Home Depot, you'll see a bunch of different metals in wires. That's what ductility means. All right, so that's bullet point number 1, bullet point number 2, and then let's go ahead with bullet point number 3. Metals are often shiny. That's not 100%, but that's most of them are shiny. That's why we use metals for jewelry, because they're very pretty. Actually, that's also why we use metals for jewelry, because they're malleable. Okay, if you think about it, you're trying to shape them into nice pieces or whatever. So most metals are shiny. There are some exceptions. We don't need to know the exceptions. But really the last bullet point is the one that really for your chemistry is going to be the most important for you to always remember. Metals will tend to lose electrons in chemical reactions with nonmetals. Now, a little bit earlier, I wasn't really prepared to say this part because we hadn't talked about this yet, but do you remember I had sodium and chlorine? Who lost the electron? It was the sodium, right? Look where sodium is. He's a metal. So that's what I'm saying. Metals will tend to be the electron losers or the electron donors, okay? Notice who he was kind of with when that happened. He was with a non-metal, chlorine. So the whole concept is that when you have a metal with a non-metal, like in the same beaker, the metal is going to lose the electron. That's always going to be a one-way deal, okay? So that's, metals will be electrons, will be losing the electrons. Now let's finish this out. We'll tend to lose electrons in chemical reactions with non-metals, and when they do, they will form, let me write the word forming, cations. When they do lose those electrons, they're going to end up becoming cations or positively charged particles, just like the sodium did. nonmetals. Let's come over here to nonmetals. It's going to be just kind of like a little bit of the opposite here. Nonmetals are poor conductors. They're not good conductors of heat or electricity. They're actually not very malleable. In fact, they're brittle. Not all of them. If they're solids, I mean, let's see here. You can almost see in this little picture, sulfur. I mean, if you look closely, doesn't that just look like if you smashed it, it would just go to a powder? And that's exactly right. That's what we mean by brittle. You can't hammer it into a nice sheet. It just kind of become a powder. Many of them are gases at room temperature. You don't need to know which ones, but, you know, starting to kind of layer your chemistry knowledge. The last column, we'll talk about these in a minute, noble gases, but many of these are gases. Most of them are gases at room temperature. Your chlorine, your fluorine, your oxygen, your nitrogen, these are gases at room temperature. So there's a lot of gases over there. And then what else do we want to say about, oh, nonmetals? Exact opposite. Nonmetals will tend to gain electrons during chemical reactions with metals. So it's the same thing, kind of like, just like the chlorine was. He was a nonmetal. He gained the electron, and that's what nonmetals will tend to do when they're partnered or when they're paired with a metal. They will be the one who receives the electron. By the way, it can be 1 electron, it can be 2 electrons. I'll put that S in parentheses. How you know how many, that comes later. That comes soon. We'll learn that actually soon, how many are transferred. But right now, just that they transfer it all is really what we're trying to say. And when they gain electrons, I hope you realize they will form, let me write the word, forming anions. Just like we talked about before, they will become negatively charged particles when they get new electrons. Now, there are some elements that live on the border, okay? So let me go ahead and do this here. These ones here that live on the border are called metalloids. Metalloids. Now, there are some really famous metalloids. Technically, I think anybody that lives on the border, you could call a metalloid, but there's some that are more famous than others. Silicon, arsenic, antimony. Okay, let me go ahead and write that. Probably silicon is the most famous. Oops, antimony, SB. All right, so these are the ones that live on the border. And just like if you think about countries, people that live, on the border between two countries, okay, so picture our southern border, will often display mixed properties in terms of culture, in terms of language, in terms of food, in terms of a bunch of different things. Of both sides of the border. And believe it or not, that's exactly what happens here. Metalloids have, I guess we can just write a few things down here, have mixed properties. I'm talking kind of the concept of Tex-Mex food. You know, it's like a mix. It's kind of Texas, kind of Mexico. Mixed properties. Now, here's the thing. The most important mixed property when it comes to these type of elements is the conductivity part. If metals are good conductors and nonmetals are poor conductors, where does that leave metalloids? Metalloids are what you call semiconductors. They're medium. They're kind of good conductors. Now, that's a really interesting concept because when something is medium, you can utilize that property for technology, for the benefit of humankind. You've all heard of Silicon Valley over in California. Well, that's not just a fun name. It's named after the fact that silicon has this semiconductor property, which allowed it to be manipulated in computers. I don't know that whole world, but chips or whatever, microchips or whatever, where you can manipulate something if it's medium. The concept is like in cooking. If I'm trying to bake a cake, I can't throw it into a fire. I won't get cake. That's too much conductivity. I can't put it on the table. That's no conductivity of heat. That's not going to cook it. I need to put it in a situation, an oven, which can be controlled. And that's the idea here of the semiconductor. So that's why they can use it for technology. Now, that's all you need to know about metalloids. I don't think I talk about it at all the rest of the semester. So that's really the only concept you want to know, kind of some famous metalloids, and really this concept of being a semiconductor. All right, so that's that. So moving on to, actually, yeah, let me erase this here. Staying on a little bit more of the geography of the periodic table. Let me leave my basic periodic table up here. Clean it up a little bit. Okay, the next thing we want to know about the periodic table is this concept of rows and columns. It's a period. Oh, sorry, it's a table. So tables have rows and tables have columns. But in chemistry, we actually don't call them rows and columns. We call them periods and groups. So the first thing is, let's talk about the rows. The rows are numbered, and these are called periods. So if I was to ask you what period is argon in, you would find argon, AR, and you would locate it in period 3. Okay, you're just looking at a periodic table. You're looking at the numbers of the rows. If I was to ask you what period iron is in, you would locate iron, and you would see that it's in period 4. So that is just looking at your periodic table. Make sure you can just know what that terminology period means for the table. In terms of the columns, so that's the rows. In terms of the columns, these are called groups. These are called groups. And just in this section over here, you'll see in your periodic table in your front cover of the textbook or the one that's on Blackboard, there's actually 2 numbering systems for your groups. One of them incorporates A's and B's. The other one goes from 1 to 18. Go ahead and either cross out mentally or physically the 1 through 18 numbering system. We don't use that in the course. I only use the system that has A's and B's. So if you were to label these 2 groups, the ones that I have on my board, you would be writing 3A and 4A. So the numbering system with the A's and the B's. So one of the most famous element in 3A would probably be aluminum. The most famous element in group 4A, let's just say carbon probably. So that's how you know, that's what a group is. If I was to ask you what group is magnesium in, hopefully you would say 2A. If I was to ask you what group chromium is in, hopefully you would say 6B. Okay, so that's the idea of periods and groups. Now, remember what Dmitry Mendeleev had discovered, okay? This is huge. Elements in the same group. That's actually why they're called groups. Elements in the same group have very similar chemical properties. That was what we were talking about with Dmitry Mendeleev. Remember when we said lithium, sodium, and potassium all exploded with water? That's what we're talking about. Remember when we said helium, neon, and argon were all unreactive and gases? So being in the same group means you're very similar to each other. So if I was to ask you, even if you don't know a whole lot about chemistry, but you're looking at a periodic table, and if I was to say which element is the most similar to copper in terms of how it acts chemically, what kind of chemical reactions it does, what kind of ions it forms, that kind of thing. You would look at copper, and the one most similar to it is not zinc, and it's not nickel. It would be silver because it's in the same group. If I was to ask you, talk to me about an element that acts like chlorine, that forms the same type of bonds as chlorine, and that has the same type of chemical reactions. You wouldn't look next to chlorine. Okay, the answer would not be sulfur, and it wouldn't be argon. It would be somebody in the same column as chlorine, a fluorine or a bromine. Okay, that is what the correct answer would be. So being in the same column means that you have similar properties. You do the same things. It's a very important concept in chemistry because once you learn that, you can actually learn, lots of different stuff, even about shapes of molecules and things. Once you learn it about one element, you can fairly safely apply it to the same elements in the same group, at least certain types of properties. So that's a really important concept. Okay, that is periods and groups. Now, main group versus transition elements. This is an important thing. It's mentioned in chapter 2, but I want you to make sure that you learn it. The main group versus transition elements actually does not have to do with the zigzag line. So I'm going to get rid of the zigzag line. Main group elements are the first 2 columns on the periodic table, the first 2 columns, and the last 6. These are your main group elements, main group. Now, why do we call main group elements main group? Main group elements, I know this is not very dark, but I wanted to use a different color. Main group elements have very predictable properties based on their position on the table. So kind of when I talk about position, I'm talking about what row they're in, what column they're in. If they're main group, they do what you expect them to do, and you can draw lots of conclusions about them. That's a hard concept to explain without examples, and we're not ready for the examples yet. So for right now, just understand main group is the first 2 columns, the last 6 columns, and that they're very predictable. They behave. You can assume a lot about them. And then that leaves us these other elements in the middle. These are called transition elements. And what you'll notice is that they actually all are, so it's in this dip down area. The transition elements all are to the left of the zigzag line. So sometimes people just call them transition metals. And that is very much true. They're all metals. This arrow here does come out of this section. So these ones down here are called the inner transition metals. You don't need to know much about these guys. In fact, we do very little in this course with these bottom 2 rows. If you just know that they're called the inner transition metals, that's going to be fine. We'll mention them later when we talk about orbitals, but that's pretty much it. Okay, transition elements or the transition metals. These have, let me just write, these are less predictable based on position. So there's less you can say by being like, oh, this element is in column 5B or whatever. It must be this. They're less predictable based on their position, and therefore there's a bit more memorization when it comes to transition metals. Once again, that's a hard concept to explain right now, but we're just going to leave it at that for now. Once we get into examples, we will have an easier time with that. Let's go ahead and now talk about group nicknames. So obviously, if you look at the periodic table, there's 18 columns. There's 18 columns. So luckily, we don't have nicknames for all the columns. Maybe they exist. Most people don't use them. But there are 4 columns or 4 groups for which the nicknames are really popular, really used widely. And let me go ahead and just give you what those ones are, the ones that you'll have to know, because it just becomes part of the vocabulary of chemistry. And you just want to be able to be proficient at this. Let's start with probably the most famous group nickname, the very last column. These are called the noble gases. The very last column. That's your helium, that's your neon, your argon. And there's one thing actually 2 things I want to say about the noble gases. I'll write it right here. The noble gases are, for the most part, there's exceptions, but they're gases at room temperature. Helium is a gas, neon is a gas. So that's why they're called the noble gases. They're gases at room temperature. But really more, maybe importantly, is that the noble gases are unreactive. And unreactive really means exactly what it says. They don't like to do chemical reactions. The helium atom is just the happiest atom on the planet. It just likes to float around by itself. It doesn't want to form compounds. It doesn't want to react with anybody. It just stays perfectly satisfied as a helium atom. And I believe that's probably why they're called noble, is because they're just contented, self-content. They don't need to form compounds with anybody. So the reason why they don't need to happens to be because they are stable all by themselves. So they're unreactive, meaning that they are stable. And we talked about this before. Stable means in a low energy state. They're happy. They're in a low energy state all by themselves. So actually, when it comes to chemical reactions, you're not really going to see a whole lot involving the noble gases. Some of these ones lower actually do form some compounds, but the heliums and the neons, they don't form, you're not going to ever see them as reactants. They just don't do it. They're self-content all by themselves, floating around doing their thing. Those are the noble gases. Let's come over here to the other side, the first column. These are called alkali metals. Alkali metals. Alkali metals, what I'd like you to know about them is that they are highly reactive. It's actually kind of like the opposite. They love to form compounds. They love to be reactants in chemical reactions. Remember I told you lithium and potassium and sodium, when you react them with water, they go through a very lively chemical reaction. So they're highly reactive. The types of chemical reactions, we'll learn them later. But for now, just they love to undergo chemical reactions. The next column in is also famous. Alkaline earth metals. Alkaline earth metals. That is your column with your calcium and your magnesium and your strontium and your barium, alkaline earth metals. Now, these are also highly reactive, but a little less highly reactive. And that's really all we'll say about them for now. They're second place to the alkali metals, okay? So they're a little bit less so. And then over here is our last group, and that is the halogens. That's your fluorine, your chlorine, bromine, and iodine. And your halogens are kind of similar to your alkali metals. Very highly reactive. Love to form compounds, okay? So that's group nicknames. Now, moving on, to the first periodic property that we want to start having in our arsenal so that we can start using it in the next chapter when we begin to talk about compounds and their names and kind of what ones form and stuff like that. The first periodic property that we want to memorize, so to speak, is ion formation. Ion formation. So let me go ahead and give you kind of the key point here. Many Mg, main group, many main group elements always form the same type of ion let me do this ... when they form ions. Okay. So the idea here is this. When you're looking at your periodic table, there is a little pattern of ion formation. It's not written on the periodic table, but you either want to write it down yourself or you just want to know it. And the idea here is this. The elements in the first group, when they form ions, they always form the same type of ion, a 1+ ion. They always form a 1+ ion. Sodium, potassium, lithium, okay? All of those will always form a 1+. Now, if I can get you to think, well, how'd they do it? They gave away 1 electron. Okay, that's another way of thinking about it. But really, for now, just think they always form a 1+. Elements in the second column always form a 2+. This is a pattern that you're going to memorize. So if you have an element in the second column that has formed an ion, then you will know it's always a 2+ ion. In other words, magnesium is not going to form a 3+ or a 1+. It's going to form a 2+ because he's in the second column. Now, let me finish the pattern first, and then we'll talk about what does this all mean. Over here, remember, this is all dealing with main group. That's why I skipped the transition. The 3+ really only applies to aluminum, where aluminum will always form the 3+, okay? The others have a little bit of variability, so we're just going to stick with aluminum. Aluminum, when he forms an ion, will always form a 3+. The noble gases, understand, they don't do any of this. So there's nothing to write above the noble gases because they don't form ions. They don't do chemical reactions. So go one in. The halogens, they will always form a 1- ion. The fluorines, the chlorines, they're always going to form 1-. When they form an ion, that's what they're going to do. They're not going to make cations. They're not going to be 2-. They're always 1-. One column in, the sulfur and the oxygen column, that's always a 2-. They're going to form 2- ions. And the next column in, the 3-, or sorry, the column with nitrogen, he's going to form a 3-. Now, the 3- really only applies to nitrogen reliably. So what I'm doing here, if you've got your book, I am essentially recreating. Let me see what this table is for. Table 2, figure 2.13. That's a very important figure. Don't miss it in your readings. Very, very important. Well, I guess phosphorus as well will form the 3-. So this is really important because that's a big, huge piece of information in your chemistry knowledge, which is going to allow you to learn a bunch about compounds and what types would form and what types wouldn't form and that kind of thing. A very simple pattern, 1+, 2+, 3+, and then skip the noble gases and go in 1-, 2-, 3-, and that's it. Now, here's the deal. Many main group elements always form the same type of ion, but only when they form ions. So how are you supposed to know when they form ions? See, because here's what a lot of students kind of get a little bit messed up on. They will see oxygen in the 2- column, and they'll think, oh, oxygen must be a 2- all the time. But the air that you're breathing, the O2 gas, is not an ion because it doesn't form ions when it's with another oxygen. Remember how I said it was O2? When it's with another oxygen, it's not going to form an ion. It's not that they always are ions. It's just when they form an ion, those are the charges. So how do you know when they're going to form an ion? And here's, it's very simple. It's great. They're going to form an ion when they're paired up with a metal, when a metal is paired up with a nonmetal. Like when those are the two species in your compound, that's when they're ions. When you have one of them with one of them. Remember, sodium and chlorine, that's when they're ions, okay? So only in that context is that really when they're going to be ions, when they're kind of paired up with one guy from the metal side and one guy from the non-metal side. That's really when you know. So if I was to ask you, there's a compound, if I was to say a compound contains the sulfur anion, what is the sulfur anion's charge? You would find sulfur and you would see that he's in the 2- column, and then you would know that he must be existing as the S2- ion, because I told you that he's existing as an ion and that must be his charge. If I was to say a compound contains lithium as an ion, you would know as soon as I say that it must be the Li+ ion, because lithium, when he forms an ion, that's going to be the charge. And by the way, most people do not do the 1. It would just do a plus. So what you want to do is commit that little pattern to memory. And honestly, as I've been talking about it, you probably already have. It's not a hard pattern, but you're going to see in the next chapter, we're going to use it a ton when we start making compounds out of these things. Alrighty, so the last thing that we want to try to accomplish in this video is the mole concept. We are going to kind of do this about halfway because you're going to learn to do more about gram to mole conversions. Actually, you know what? Now that I just realized it, this, the mole concept is something that I think I will wait on because I believe, actually, you know what? Let me start on it. Let me do a little bit on the mole concept just to get you started, because you're going to complete this in the moles and molarity lab, which is going to come later, but it comes in several weeks and I think you need a little bit now. So let's do what is a mole and kind of how to use it to convert between different things. So let me go ahead and give you a little bit on the mole. The mole. It used to drive me crazy because I don't think I ever had someone explain it to me when I first started learning chemistry. I could use it. I didn't know what in the world it was. It drove me nuts. Now that I know what it is, it's no big deal. It's the easiest thing in the world. So let's see if I can do a better job than I had when I had it first of what is a mole. Okay, so first of all, let me go ahead and write that question. What is a mole? The key thing is to understand, the answer to this question is the mole is similar in concept. Similar, not the same. Okay, some people have obsessed with that and they think it's the exact same. It's not the same. It's similar in concept to the word dozen. Okay, and that is such an important thing to lay at the groundwork because everybody knows what a dozen means, okay? A dozen is just representing 12 of anything. I can count donuts by the dozen. I can count pencils by the dozen. You're just counting 12 of something. So let me just, I'll just do 12 circles. 5, 6, 7, 8, 9, 10, 11, 12. There you go, a dozen circles. Conceptually, the mole is the exact same thing. You're just counting, but you're counting a much bigger number. 6.022 times 10 to the 23rd of anything. So understand that 6.022 times 10 to the 23rd is me taking this decimal place and moving it 23 spaces. So you pass million, you pass billion, you pass trillion, you're into whatever. It's huge. So understand that if I was to try to draw a mole of circles, I would do it for the rest of my life. Okay, it's just a much bigger number. Okay, I'm just trying to make my point here, so let me just make my point here. Let me just write etc. It's a huge number, but at the end of the day, you're just the same thing. It's just counting by chunks. If you count by the dozen, you're counting 12 at a time. If you count by moles, you're counting 6.022 times 10 to the 23rd at a time. Now, why would anyone ever do that? That seems bizarre. Well, think about it conceptually here. When do you use the word dozen? I don't count houses by the dozen. I have one house. I count very small things by the dozen. Munchkins, pencils, small things, because it's easier, because they're so small, you don't want to count them individually. So you count small things using these kind of counters, dozen. Well, when we are counting the smallest things ever, atoms, dozen is useless. That's only counting 12 at a time. I want to count by a much bigger number because the particles are much, much smaller. So I want to be able to count by a bigger chunk. And that is exactly why we use the mole. So when we use the mole, really, technically it's of anything, but we are counting 6.022 times 10 to the 23rd. Particles is a general word, but at the end of the day, you're either counting one of two things. You're either counting atoms or you're counting molecules. That's really what we're counting, but very small things. That's why you use a huge number. So that's the first thing what a mole is. Now, at the end of the day, let's do a little practice question here. One of the things that you would want to be able to do is to convert between oh, by the way, a mole is just simply a unit. It's just a unit. It's a unit of quantity. You're counting things that are discrete. And all units are man-made. The person who invented the mole was called Avogadro. That's why they call this Avogadro's number. But at the end of the day, it's just a unit. So let me go ahead and put a little practice question up and show you one way to think about this. How many iron atoms are in 0.12 moles of iron? How many iron atoms are in 0.12 moles of iron? Well, the way that I would handle it is this. If I only have one number in my question, I always start it like this, 0.12 moles of iron, but I'll just leave out the iron now. The way that I always do this is through the use of a conversion factor. So in the other video on SI units and metric conversions, I introduced this concept of conversion factors. I would use one here. Remember, to use a conversion factor, you're multiplying it by a number by a conversion factor. And you're just trying to convert it from one unit to the other without changing the amount. So notice, I'm starting with moles, but I want to convert it to atoms, number of atoms. And the conversion factor that I would always use to go from moles to number of atoms, or number of molecules, depending on what the question is about, is that in every 1 mole, and I put that on the bottom so it will cancel, there are 6.022 times 10 to the 23rd atoms. And that is, I would just call it like the Avogadro's number conversion factor. It's always the same. Sometimes you use it right side up, sometimes you'll use it upside down, depending on what number you start with. But notice how moles will cancel. This is a valid conversion factor because this represents the same amount of this. A mole is this many. See, that's what a mole is. It's this many particles. A mole is this many. So now I would just take it to my calculator. This unit is gone, atoms survives, and now I'll be able to know how many atoms there are. 0.12 times 6.022 times 10 to the 23rd, and I'm getting 7.2 times 10 to the 22nd atoms, and that would be the right answer. So that's converting between moles and atoms. You just use this Avogadro's number conversion factor. Let me proceed on to just kind of wrap this up about, and bring this all the way to molar mass, because this is really where the whole concept of the mole is the most useful. This is useful, but there's something even more useful. The mole, the question is, where did that number come from? It's such a bizarre number. You would think that if it were me, I would just be like, oh, okay, I get it. Let's count by bigger chunks, but let's count by 100 billion or a trillion. That would make more sense to me. But it's not. It's this weird number, 6.022 times 10 to the 23rd. Where did it come from? So before I tell you that, I need to spend a tiny bit of, just a minute or so, coming back to this very mysterious AMU. I've been using it the whole course, or at least much of the course. I've told you that it's the atomic mass unit, and that it was invented to count really small things like protons, neutrons, or atoms, to count their mass, to weigh their mass. It's much, much smaller than a gram. What is it though? I mean, every unit must have a standard somewhere. Like, where did it come from? Like, what does it represent? Here's the thing. 1 AMU is exactly 1/12 the mass of a C12 atom. Now, see, we have enough information now. See, I had to teach you what this was first. That's why it didn't come right away. Things have to kind of get layered. Remember, C12 is the isotope of carbon that has 6 protons. Let me make them black. And 6 neutrons. And 6 electrons, but let's just talk about the part that weighs a lot, the nucleus. That's C12. So what was decided was that however much C12 weighs, we're going to take 1/12 of that, and that's what we're calling an AMU. So that's why when we say a proton or a neutron weighs about 1, it's because it's 1/12 of what this is. Okay, so that's what an AMU is. It's exactly 1/12 the mass of a C12 atom. C12 was the standard for AMU. That's important. It was that particular isotope that the whole concept of AMU is wrapped around. Now, with this, let's have a little relationship here. Are you with me that 1 C12 atom weighs, or you could say one C12 atom weighs 12.000 AMUs. Okay, are you with me on that? Or another way, that actually probably the better way to write it, now that I think about it, is the other way. Let's write it upside down, because then you can use the word per. There are 12.000, perfectly 12 AMUs per atom for C12, okay? That is a true statement. So now coming to Mr. Avogadro, where did the mole come from? Avogadro basically said that, or he found that 6.022 times 10 to the 23rd is the exact number of atoms in 12 grams of C12. So I don't know how he did it, but he had exactly 12 grams of this exact same isotope, C12, and he has the number of atoms in it. That's the number. So how does this all come together? I know it's really kind of hard to grasp, but let's kind of try to at least have this little light bulb moment. For C12, this particular isotope of carbon, now we have two relationships. There are 12, I'll leave out the 0.00. There's 12 AMUs per atom, but also there are 12 grams per mole, because that's what he defined the mole to match 12 grams. So Here's where it all comes together here. This thing here is what you call the atomic mass. Atomic mass is mass of an atom. Atomic mass. For C12, this is the atomic mass, 12 AMUs per atom. But it's also, there's another type of mass, and this thing here is called the molar mass. Molar mass. The mass of a mole. For C12, this is the mass of the mole. The whole thing here is that Avogadro forced this relationship. He made this number be this number so that for C12, but really for everything, the atomic mass will always equal the molar mass. He wanted those numbers to be equal. He forced it that way. That's why he picked 12 grams, because he knew that this was 12. And then he counted the number of atoms in it, so that therefore the molar mass would equal the atomic mass. Now, that might not seem like a big deal, but it's hugely powerful. Let me go ahead and just show you how powerful it indeed is. And then we'll be done here. When you go to a periodic table, let's come back to carbon. And you see that number down there. There's two things that that number tells you. We have so far only talked about atomic mass. This does tell you that the average mass of an atom is 12.01 AMUs. It does. That's the average mass of a carbon atom. That's what we call the atomic mass, the mass of an atom. It's the average mass of a carbon atom based on the isotopes. But probably even more practically is another way of looking at that exact same number. There are 12.01 grams per mole of carbon atoms. That is what we call the molar mass. The two numbers, that's molar mass and it's atomic mass. It's both. The difference is what unit you attach to it. If you're using it as atomic mass, it's AMUs per atom because it's the mass of an atom in AMUs. If you're using it as molar mass, it's the mass of a mole, grams per mole. Why is this a big deal? It's huge, and if you just stay with me just a little bit longer, I know this is going long, so much should click. If I was to take this pencil graphite, break off a piece of it, there is a very simple way for me to count the number of atoms in it. I can't even see the atoms, but I can tell you with a pretty good specificity how many atoms are in it. So just take this little mental piece with me. I'm going to break off a piece of this graphite. My pencil lead. It's all carbon atoms. I usually do this in the lab. Obviously, we're not in the lab. If you go and weigh that carbon, just put it on a balance and weigh it. Let's say that it weighs 0.05 grams. Okay, let's just say that it weighs 0.05 grams. Once I weigh it, that's all I really need to know to tell you how many atoms are in it. Let me show you how. If it's pure carbon, all I need to do is do what's called a gram to mole conversion. That being the molar mass, 12.01 grams per mole, I use that as a conversion factor. Stick some parentheses around it, and now it looks like a conversion factor. Now, I'm going to use it. You tell me, right side up or upside down? I'm trying to cancel out grams because that's the unit I have right now, but I'm trying to figure out, maybe I need to be more clear. I'm trying to figure out how many atoms are in this thing. That's the unit I want. So I'm going to write it upside down. Grams per mole. It's just using the molar mass, but upside down. Grams cancels. Now, do you remember the other conversion factor, the Avogadro's number conversion factor? That will tell me the number of atoms in a mole. So I'm just going to use that one here. In every 1 mole, I'm putting that on the bottom because I want him to cancel, there are 6.022 times 10 to the 23rd atoms. And now my surviving unit is atoms. And now maybe a light bulb goes off and you can see the power of Avogadro's number of the mole. Because just by weighing a little piece of carbon, I can now calculate how many atoms are in it, things I cannot see. I cannot count with a piece of tweezers, But by weighing it, I can figure out how many atoms there are by just these two relationships, molar mass and Avogadro's number, the number per mole. So let's go see, 0.05 divided by 12.01, answer, times 6.022 times 10 to the 23rd. And I'm getting that in that little piece of pencil graphite, there are 2.5 times 10 to the 21st atoms. Huge step in our abilities as chemists if you can understand how valuable that is. By weighing something, I know how many atoms are in it. It was only possible because Mr. Avogadro invented the concept of a mole, made it match the atomic mass so we can use our periodic table, and knew how many atoms were in it. It's brilliant. You're going to use it a lot. I'm going to stop because this video has been long. Thank you for your attention. It was a long one, but so important, and hopefully it was helpful. All right, have a good day.